Hey everybody, welcome to today's webinar. Today we'll be talking about our selective detectors that OI Analytical, a Xylem brand, offers. These are detectors for gas chromatography systems, and the two detectors that we're going to talk about today are the pulsed flame photometric detector and the halogen selective detector. My name is Jacob Woodside. I've been with Xylem for almost 4 years now. I'm an associate product manager for TOC and our gas chromatography products. And I'm super excited to get into today's presentation. So with that, we'll go ahead and get started. Okay, so I wanted to pause briefly on this slide, just in case anyone is unfamiliar with gas chromatography, and really break it down into two simple terms: vaporization and detection. So I've got a couple slides here that talk about what a gas chromatography system looks like. The first slide is a 2D drawing image, and the next slide is an actual system photograph. But I wanted to lay this out in kind of a 2D form so that we could get a good description of everything that's going on here. So gas chromatography is an analytical method that's used to separate, identify, and quantify individual components in complex mixtures. And despite its name of gas chromatography, we're actually mainly testing liquid samples that sometimes have a solid or sludge consistency. The term gas in this instance refers to the carrier gas that moves the vaporite sample through the instrument. And so in order for GC to work, during the introduction phase, the compounds that must be vaporized without completely breaking down during sample introduction. And most often the carrier gas is helium, hydrogen, or nitrogen. So we're moving compounds through a column across there and onto a detector. And in the next slide, I'll discuss what happens inside the column and give you a whole overview of everything GC. So how this system operates. So the sample is first introduced into the GC via the heated inlet. Oftentimes this is done using an autosampler, or it can be done manually with a syringe. The rapidly heated sample is instantly vaporized and passes through the system, pushed by the carrier gas, also known as the mobile phase, before reaching the system's column inside the oven. The column is known as the stationary phase, and as I said, most often the column is inside the oven, always. So you're injecting samples, they're being rapidly vaporized, pushed through this column. There, the molecules are separated based on how they interact with the column. So considering the target analyte is very important when selecting the proper column for your analysis. There's this rule that like separates like, so it's important if you're separating nonpolar analytes to use a nonpolar column, or a polar analyte to use a polar column. So these compounds, they elute across the column, and then they interact with the column. And how long it takes them to interact with this column, also known as the stationary phase, is something known as their retention time. So each of these compounds have a different retention time. They're moving across the column towards the detector, and eventually they pass from the column as a part of the GC effluent onto the detector. There, they are detected in a variety of ways, which we'll discuss, but ultimately what happens is a signal is produced, and a chromatogram, which represents the peak of the current generated from the detector against its retention time, is displayed. So you have a peak on a graph that's showing current generated versus retention time, and how much area underneath that peak gives you information about the concentration of a compound within a sample. If there's more area, there's more concentration. If there's less area underneath the peak, there's less concentration. So that is everything with gas chromatography. And what you can do from there is you can check your chromatogram against existing chromatograms to determine what is present specifically within a sample. And you could also do further mass spectrometry to further speciate compounds. We won't be talking about MS in this presentation, but that is another analytical tool that's often paired with GC analysis. So in this presentation, we're specifically talking about our third-party selective detectors. Xylem and OI Analytical is not a GC manufacturer, but we do manufacture selective detectors that are add-ons to existing GC systems. And these detectors are used because they allow an end user to specifically target compounds and achieve selectivity via several different ways, which we'll discuss. The two selective detectors that we're discussing in this presentation are the XSD, featured above, and the PFPD, featured below. So there are several advantages and considerations to selective detection. It's going to reduce your sample preparation as well as the interference that you see. There's a better signal to noise ratio, so it's just easier to quantitate and reduce turnaround time on particular analysis for a target compound. Those are the major advantages. The main thing to consider as well is selectivity and sensitivity. I'm actually going to go back to that slide. So selectivity is the ability to preferentially detect one type or class of compound over another. And this is usually expressed in a relative to hydrocarbon ratio. For example, we have a chlorine versus hydrocarbon background. So that's selectively looking for a compound over another. But then there's also sensitivity, which is the ability to detect species at low concentrations themselves. So sensitivity is just detecting a low amount. Selectivity is one compound versus another. Now we can move on to the first detector, the 5383 pulsed flame photometric detector. The PFPD is a uniquely robust, highly configurable, and extremely reliable selective detector. Xylem has sold hundreds of this unit to laboratories in over 50 countries across the world, and they rely on this technology for accurate analysis of sulfur species in petrochemicals, in organophosphorus pesticides and food samples, or sulfur other aromatic compounds in flavors and fragrance extracts. This product is the industry standard for testing oil and natural gas for sulfur. Understanding this product requires detailed explanation on its operation, assembly, and options, as this detector can be configured for a wide variety of applications and methods. So before we go into what makes the PFPD, I think it's helpful to get kind of an overview of the traditional FPD versus the pulsed flame photometric detector and what separates them. So before we look at what separates them, they're actually very similar in practice. In both cases, the combustion gas is a mixture of ultra high purity hydrogen and air. And as analytes are coming from a GC, they are combusted within a flame. And these combustion products and emitting species that are formed are identical in both detectors. The main difference here is that while the FPD has a continuous static flame, the PFPD pulses a flame at a set frequency throughout the body of its detector. And so to achieve selectivity between different elements, a traditional FPD would use a combination of a physical barrier or a light shield with an interference optical filter. And by comparison, the pulsing of the flame in the PFPD actually produces a time-dependent emissions for each element, which we then electronically gate in the software to enhance selectivity. So this allows us to not only make use of a broadband light filter and a photomultiplier tube, but then we can add an element of electronic time gating to really focus in on an emission. And that's what makes the PFPD stand out compared to traditional technology. So I briefly covered some of the applications, but by far and away, the most popular application is in petrochemical processing. There's a standard method, ASTM D6228, that calls out the PFPD specifically for sulfur analysis in oil and natural gas samples. There are all sorts of different oils and natural gases that are being used. Biofuels are becoming more prevalent. There's propane, ethane, ethylene, propylene, all sorts of different fuels that the PFPD can be used for. There's also pesticides. So the PFPD, it's primarily a sulfur and phosphorus detector. And organophosphorus pesticides are very widely used in the agriculture industry, so this is another common application. And finally, there's the foods and flavoring industry. For example, in coffee, whiskey, and rum, sulfur compounds are very much responsible for distinctive flavors and fragrances in many foods and beverages, so that's another application there. So it provides some distinct advantages over static FPD, including a 10 times increase in selectivity for sulfur specifically. a 10 times increase in sensitivity. It features a linear equimolar response. This makes calibrations easier and provides the ability to quantify the concentration or sulfur in an unknown peak. There's minimal maintenance because this detector is pulsing at such a high heat, it's actually self-cleaning. There's no sort of coking or buildup of any sort of soot that happens. It's just pulsing at a very high heat. So it's self-cleaning. You have minimal maintenance. Because it's not a constant flame, you're just propagating the flame. You're using less gas than a traditional FPD as well. So there's several distinct advantages that make this detector ergonomic, flexible, and stable. Now we can go into specifically the components of a PFPD and everything that should arrive when you order one. So first, it's important to break out the detector assembly itself. This is what was pictured on the very first slide, the two detectors themselves. This is everything that's inside of the PFPD. So we've got the base assembly. You have connection ports for your gases, for your electronics. You have an igniter. You have a quartz combustor where the actual combustion reaction takes place. You'd have a light filter where you're filtering out certain light wavelengths, and then a photomultiplier tube where you're enhancing certain light wavelengths, and then a electrometer that's converting that signal to a readable measurement by our software so that you can actually see the results that it detects. And how it controls everything is with these two controllers. So the two controller boxes come with your detector. And on the right, we have our electronics controller. This is going to house the electronics for controlling of the photomultiplier tube voltage, the igniter current, as well as general signal processing. We then, on the left, have our pneumatics controller, and this houses the gas mixing assemblies. So for a detector, the flow controls can be either manual mass flow controllers, which are housed inside this pneumatics controller, or there are electronics flow controls housed inside a GC. So if you have a GC that has flow controls, you wouldn't need a pneumatics controller. If you don't have a pneumatics controller, then you would need one. The other portion I should say that comes with the PFPD is our software. The software is split into two parts. The first part here is PulseView Monitor. PulseView Monitor is our PFPD user interface software, which is a Windows-based software program that is used to control PFPD settings, display the pulse graphs, and capture data for further analysis. Finally, there's PulseView Analyzer. This is a complementary software program which allows you to retrieve and review collected pulse data and optimize settings for future analysis. So here is kind of a cross-section of the detector assembly. And now we'll go through the principle of operation and understanding the actual pulse cycle that happens inside the PFPD. We can break this pulse cycle down into 5 different phases. This slide shows a cross-section of each one of those phases, which we'll go into later. But the important thing to remember here is that we have a very high temperature flame and a pretty rapid pulsing frequency of 3 to 4 hertz. Kind of before we get into each cross-section, I guess I can identify some critical areas. So cross-section of the detector body. We have gas lines down here in blue and purple. These are mounted in the base. We have the glass combustion chamber in the center. And then the ignition source, or the igniter, which is mounted in the cap of the detector. Phase 1 is known as filling. This is when the combustible mixture of hydrogen and air, shown in blue and purple respectively, fill the detector body, combustor, and cap from the bottom up. The wall gas is shown in blue. This is air-rich and fills the portion of the detector body outside. And the purple gas, this will be the hydrogen-rich gas that is filling up the rest of the detector. So you have the filling of gas, then you have the ignition of the igniter within the cap. So when the air-rich gas mixture reaches the glowing coil, it begins to burn. And for anybody who has a PFPD, this is the sound of the popping that you hear is the igniting of the gas mixture. Phase 3 is propagation. During phase 3, the flame travels back through the cap along its original pathway, consuming the hydrogen and air fuel along the way. During phase 4, the flame passes through the combustion chamber where the gas mixture changes from air-rich to hydrogen-rich. As the target compounds elute from the GC column, they are combusted in the flame, forming emitting species, which then begin to fluoresce. And so fluorescence is a very important part of this detector. So really what happens in fluorescence chemistry, it's involving the absorption of light, the excitation of electrons, and subsequent emission of light at a longer wavelength due to energy loss. And photometric detection here utilizes light. We're making use of that light to provide an estimated peak that determines the total concentration. So yeah, there's important notes that I have here as well, which are detailed in application notes, which we have, like, for example, our excited species that are formed. There's more information on this, but that's in general what's happening. We're fluorescing a compound and then moving that signal across a photomultiplier tube in a filter. Phase 5 is the extinction of that flame. So the flame is extinguished when it reaches the bottom of the detector and all gas has been consumed. This takes approximately 4 milliseconds for the flame to travel from the igniter down to the bottom. And even though the flame has been extinguished, many of these emitting compounds will continue to fluoresce. So after extinction, this is when the pulse cycle happens again. And that is the entire principle of operation. So I mentioned earlier something about the time domain that the pulsing cycle adds. So what this means is that emissions from individual species formed in the flame are separated in time, and each emitting species has a different characteristic lifetime within the combustion chamber of the detector. The specific lifetime for each emitting species sometimes is known as the delay. So that is really important. Individual hydrocarbon and heteroatoms emissions are separated, and here's kind of a rough guideline for the delay for our target compounds in the PFPD. Hydrocarbon just typically is your background, so that's important to know. And then the two most common target compounds would be phosphorus and sulfur. Phosphorus emitting a little bit sooner than the sulfur. So this is a depiction of what happens after the detector goes through a light filter, through a photomultiplier tube, and then an analog signal is magnified, sent to the electronics inside the detector controller. Then we see a peak in our pulse view monitor software. So now we can look at pulse view monitor, and this slide shows a screen capture of pulse view monitor. So what we're seeing here, the x-axis is displaying time in milliseconds, and the y-axis is displaying the intensity of the photomultiplier tube in counts. So when we're looking at this peak here, this would be a sulfur peak that we're targeting. And what I said on the last slide about each emitting species having a different time of emission. So we know sulfur is 6 to 25. We know that hydrocarbon background is 1 to 3. So this is our little peak here, is our hydrocarbon background. Our main sulfur peak is right here. So what we can do then with pulse view monitor is apply an electronic gate. What we do is we filter out everything that is outside of our desired portion of emission, aka in this example, 6 to 25 milliseconds. We're going to electronically filter out everything else, and this is going to increase our sensitivity versus background by tenfold. Therefore, we would be having each pulse is going to, this is going to increase your selectivity and sensitivity because you have completely focused sulfur emissions. You have no noise in the background. So that is the value of electronic gating. Now, the other important thing here is because we're working with a digital signal, we have actually the ability to provide or apply rather 2 simultaneous gates, resulting in 2 simultaneous chromatograms. This would require a second analog input board so that an operator would be able to see a second channel. But that is a very handy feature if you want selectivity on your sulfur signal and then your hydrocarbon signal as well. You can produce two simultaneous mutually selective chromatograms for both elements. So usually when it comes to a detector, the first specification that people want to know is sensitivity. And sometimes this is defined as detectivity, but this may not have a practical meaning for an end user just because of the customizable nature of GC. So we put a detectivity limit here, and you can see it there, but really what it comes down to is depending on your injection, your inlet that's used in your GC, your column, the split ratio of your inlet, and also the detector and how well optimized the detector is. So it's a very customizable process. That's why we list a detectivity limit, in particular on application notes, but providing a general detection limit is hard to do in some cases. It's just dependent on the application and everything else in the system. So selectivity on the PFPD, primarily the result of two variables, our time-separated emissions and our electronic gating, but also our selective optical filters, which we haven't really talked about. I have another slide that shows which optical filters are used, but here in the notes I have that a BG12 broadband optical filter is used for phosphorus, for sulfur, and then a GG495 broadband filter for phosphorus. Other parameters that can be adjusted include your gas flow ratio, the size of your combustor, the temperature of your detector, and the selection of the photomultiplier tube. So it's a very customizable system, which is why we detail parameters in our application notes so that an end user can replicate the data that we're seeing with the same configuration. So selectivity, it's a quantitative measurement, how selective we can be with sulfur or phosphorus without interference. Here's kind of a rough guideline. But again, selectivity is going to be adjustable. And yeah, depending on how well you set up your system, how well you're limiting the amount of noise, you could have, in theory, up to unlimited selectivity. In practice, this is not so common. So this is helpful for anybody who's customizing this. These are the board and channel parameters that you would actually go in the software and change if you were changing the type of analysis you were doing. Yeah, all sorts of different things that you can set there. We also have our gate parameters. This would be changed again on the target compound. So we have our start and stop time. In this instance, it's 6 to 24, sometimes 6 to 25. But it's just dependent on the end user and what they're looking for. So here are comparison for sulfur and phosphorus, how to optimize the PFPD. We're the same here, but a little more detailed information. Also can do nitrogen and other elements on this. Those are less common than sulfur and phosphorus. Okay, in this slide, I wanted to show you an example chromatogram. So this is actually two chromatograms. We have a sulfur signal and a hydrocarbon signal. And what I want to show on this slide is that we're actually seeing a ton of hydrocarbon background to start with. The detector actually is saturated. So our peaks are coming down from the top. This means our hydrocarbon content is completely saturated. In a normal detector, you would have a very difficult time detecting sulfur in that hydrocarbon background. However, because of things like our electronic gating and our broadband filters, we can still see down to 5 ppm total sulfur even in this intense hydrocarbon background. So really, this slide is just demonstrating how selective this detector can be for sulfur. And same kind of thing here. So this is definitely less hydrocarbon, and this is actually diluted sample here. So with a high split ratio as well, we're getting down to some low total sulfur levels. So yeah. There's also thiophene and benzene. There are two ASTM methods there. This is a very common application now. And a couple more chromatograms with some low sulfur columns. This is for low-level sulfurs in feedstocks. This is important because sulfur poisons catalysts and corrodes equipment in the petrochemical industry. They want to monitor for sulfur. That's why they do this testing. This is sulfur and propylene propane. And here is a detector comparison for sulfur and phosphorus with some existing technologies that are out there. We have traditional static flame photometric detection, a flame photometric detector with an electronic pressure controller. Then we have our detector, the OI 5383 PFPD, and then we have a sulfur chemiluminescence detector with an electronic pressure controller. So you can see here that without compromising selectivity, and while adding a linear response feature, which that allows you to produce an equimolar response, you're still getting just as great detection results, and you can do simultaneous mutually selective chromatograms with a single detector. So when you look at something like cost, for example, you're saving a lot in the long run. And on top of that, it's selective for both sulfur and phosphorus. So yeah, this is essentially the overview for the PFPD. If you have any questions, please feel free to write them in the chat. I'm going to go ahead and start with the next detector, but at the end of this presentation, I'll have time for any and all questions. Take a drink of water. All right. So the next detector that we're going to talk about is the 5370 XSD. And if you're familiar with our products, you might be familiar with the 5360 XSD. We're excited to announce that next month we will be releasing the 5370 XSD. This is an updated version of this detector. Not too much has changed in terms of performance, but we do have an all-new electronics controller that is backwards compatible with the XSD and existing ELCD models out there. We also have now one item instead of several, and this one item will have configurable base assembly with different brackets depending on which GC can be used. So we're very excited to announce this. We've been updating a lot of our content and our manuals as well. So please keep an eye out for that to release here by the end of September. But this is a little sneak peek. It's the same overall detector. It's the same detector itself. So we're still looking at halogen compounds. So that's what the XSD does. The XSD offers the safest way to analyze halogen-containing compounds on a GC. It's unique in the fact that it doesn't contain radioactive sources or use organic solvents like other halogen selective detectors. This would eliminate the need for catalyst tubes, resin cartridges, and reduce the amount of maintenance. So this is another very selective detector, minimizes the need for sample preparation just due to its sensitivity, and it's sensitive to chlorinated, brominated, and fluorinated compounds in that order. It has a unique jet design that minimizes peak tailing due to unswept dead volumes, and this detector actually requires only air to operate. New with this 5370 is that every detector now has the enhanced venting, so this is no longer an option. Every detector comes standard with enhanced venting. This diverts solvent away before entry into the reactor core. So this is another industry standard for testing oil, for testing pesticides, organochlorine pesticides, and we will go into the operation, assembly, applications, and some example chromatograms of this detector. So it's used to detect primarily chlorinated compounds. It's just due to the design, it's very sensitive to chlorinated compounds, and we'll talk about the exact numbers later. But in terms of the actual items that you receive, this consists of two principal components. On the right, we have our Model 5370 detector assembly, and on the left, we have the Model 5300 detector controller. So similar principle in that this is an electronics controller. We're routing a 0 to 1 volt signal output from the controller to the GC, from the GC system through an analog input board to the detector. So the XSD, very sensitive to chlorinated compounds. Reformates are produced as a byproduct of crude oil distillation, and organic chlorides can form as a consequence and cause corrosion, poisoning of catalysts downstream in the petrochemical refining process. So any sort of chlorinated species in petrochemical processing or in organochlorinated pesticides would be able to be detected by this detector. Okay, so this is a little overwhelming at first, but essentially I wanted to break down what happens inside the XSD into three major steps. And those steps are oxidative pyrolysis, ionization, and thermionic electron emission. And I know, especially that last one is a bit of a word salad. So I'm going to briefly explain what those terms mean, just in case you're not familiar. And then we'll go into the steps of how those terms apply to what's happening inside the XSD. So oxidative pyrolysis. This is the process where organic materials are broken down at high temperatures in the presence of a controlled amount of oxygen. So oxidative pyrolysis involves oxygen influencing the reaction pathways and product distribution. And you may be asking, how is this different than combustion? Combustion is a complete chemical reaction. Oxidative pyrolysis is thermal degradation of the material because of oxygen. So you can think of it as an incomplete combustion. This is just oxygen's present impact on thermochemically decomposing a material. Okay. Ionization is the process where a neutral atom or molecule gains or loses electrons, resulting in a charged particle called an ion. So a common ionic reaction is table salt. The ionic compound is formed, sodium chloride. Sodium loses an electron, becomes positive sodium ion. Chlorine gains an electron, becomes a negative chlorine ion. They form table salt. Ionization is actually the reason why radiation like X-rays or gamma rays are so dangerous. These waves are so powerful that they carry enough energy to knock electrons out of atoms or molecules, causing them to ionize. This disrupts the structure and function of molecules like DNA. And finally, thermionic electron emission. This is the process in which electrons are emitted due to an increase in temperature. So thermionic, increasing temperature, electron emission, causing electrons to emit. The material, often metal, is heated to a high temperature, causing electrons within it to gain enough kinetic energy to break free and enter the surrounding space. And a common example of this is actually a vacuum tube that's found in radio tubes or old CRT televisions. You have in these devices, you have a filament that's heated by passing an electric current through it. The heated filament then emits electrons, which are controlled by electric fields and produce or amplify signals or display images. Really cool stuff. So those are the three chemical principles that are happening inside of an XSD. Now we can go through and explain when and where they're happening. And actually, before we go to the next slide, it's important to know that these first two images are kind of happening simultaneously because of the high temperature of the reactor. But I'm going to start with oxidative pyrolysis. So the very first thing that happens is that the reactor core is heated to 1,000 or 1,100 degrees Celsius. Very, very hot. Then we have effluent coming from the column that is mixed with air. And this mixture is passed through the reactor core. Now, the GC effluent contains our target compounds. So those analytes undergo oxidative pyrolysis. It's so hot and there's so much oxygen that the stream is actually almost reaching a plasma-like consistency, and it's converting halogenated compounds into free halogen atoms. So you have a heated reactor core, you're mixing in air and GC effluent, you're basically pyrolyzing the release of free halogen atoms and other byproducts. Now keep in mind, inside this reactor core is very, very hot. And in the reactor core, there's a ceramic probe that has an electrode, which an electrode has an anodic side, a cathodic side. In this case, it's a platinum wire and a platinum bead. we have an increase in temperature. So while this oxidative pyrolysis is happening, there's also the release of potassium ions from the anodic wire that accumulate on the platinum bead cathode and form an alkali monolayer. This alkali monolayer allows the free halogen atoms to combine with that surface and reduce them to halide ions. So we're pyrolyzing an effluent, we're releasing ions to a cathode. The temperature, the released free halogen atoms collide with that cathodic surface and release more ions. The energy of this reaction is then raising the temperature of the cathode, which is then causing thermionic electron emission. So we have the release of atoms, the accumulation of atoms via ions on this bead, and then the heat releasing those electrons. The current is then measured, and then that is converted via electrometer to a voltage output, which then corresponds to a peak in your software. So that is how the XSD operates. And here it is one final time in all its steps: pyrolyzing, converting them to halogen atoms. They're reacting, they're accumulating on an alkali monolayer cathode. Then they're being released due to the heat of that reaction, and the current is measured. And so these are our specifications and our performance requirements. Similar kind of thing when it comes to the range and sensitivity and detectivity. It's very customizable. But the really important thing to note on this slide is the relative halogen sensitivity. This is something that's true just because of the nature of each of those compounds. Chlorine is just more reactive. It works better in our system in terms of detection. So fluorinated compounds have actually 100 times the sensitivity of fluorinated compounds and 10 times the sensitivity of brominated compounds. And this slide is showing exactly that. So we've got three benzene halogen compounds: fluorobenzene, chlorobenzene, and bromobenzene. We can see that our chlorobenzene response is way higher than our bromobenzene, which is dramatically higher than our fluorobenzene response. So recently there's been an increase in interest in the detection and removal of organic chloride species from petroleum products. You have crude oil that's distilled to form naphthas. And then with continued refining, those products go through catalytic reforming. They produce reformates. They're used in many products. These reformates are used in many products, including gasoline blending stock and aromatic bulk chemicals, so that it's a crucial process. And during that process, catalysts are conditioned with organic chlorides. And if you don't remove those organic chlorides, they can cause corrosion and poisoning catalysts for petroleum refineries. So this is an example chromatogram running a 20 ppm standard on the XSD for petroleum products. You can see we're getting good response. And here's a similar situation for pesticides. We have organochlorine pesticides that are used in a variety of sample matrices: food, water, and soil. Toxic pesticide residues can persist in the environment. There are also polychlorinated biphenyls that were once used in transformer oils because of their desirable chemical and physical properties. These are another class of persistent compounds that are considered toxic. So EPA method 608, 608.1, 2, and 3, they have been available for many years and outline halogen-specific detection on a GC system for pesticides and PCBs. And with that, we have reached the end of the presentation. So at this time, I will go ahead and answer any questions that you may have. I'm not seeing any immediately in the chat. I'm going to hang on here for just a couple minutes to give anybody some time. If you have a question, feel free to reach out. Perhaps I can put my email in the chat in case you do have a question. Feel free to reach out. We'll go ahead and hang on here for just a couple minutes. If you have to run to your next meeting, just want to say thank you so much for your time. I really appreciate it, and have a great rest of your week. But if you do have a question, I'll hang on till about 11:45. or maybe sooner if everybody's dropping off. Okay. Looks like I see a question here. So one shortcoming of the FPD is its non-linear response. What is the linear range of the PFPD? That is a good question. I believe I have it listed here somewhere. Let's see. Not on that slide. See if I can find it here. Aha. So it is going to depend on your target analyte. But what we list as our linear range is 2.4 orders here for sulfur, and then around 5 orders for phosphorus. Oh, yes, good point. Thank you for putting that in there. Yes, if you have any, if there's anything I didn't answer on this webinar, if you have any additional questions, please visit our web pages. Please feel free to send me an email, and we will do our best to get back to you as soon as we can. All right. Well, I'm not seeing any more questions, so I'm going to go ahead and wrap it up. If you have anything, please just let me know. Thank you all for joining so much, and have a great day.